So gases and chemical reactions. We've seen gas evolution reactions where a gas is generated. There are many other types of reactions where gases may be consumed. All of the reactants and products might be gases. When we have gaseous reactants or products, the amount of gas is not usually given in moles. I mean, it's not usually given in moles. It's also not given in grams. We're accustomed to seeing things given in grams. Oh, grams of this and grams of this and how many grams of that. Gases are hard to weigh, right? You could do it, but it's not easy. So we often give amount of gas in terms of its volume, its pressure, and its temperature. So we can use the ideal gas law to convert pressure, volume, and temperature into moles. So the ideal gas law is PV equals nRT. If we want to solve for moles, we divide both sides by RT. And so N is equal to PV over RT. That's what the first question on the pre-lab was asking it to do. That's all it was asking it to do. Solve the equation, rearrange the equation for N. So there, I gave you an answer. So from pressure, volume, and temperature, we can find the moles of gas. And then we can jump into stoichiometry. We said grams to moles to moles to grams. So we're going to skip the grams, and we're going to go to moles after we finish this calculation. In this reaction, 4.58 liters of oxygen were formed at 745 millimeters of mercury and 308 Kelvin. How many grams of silver oxide decomposed? Use the balanced chemical equation to organize this. So oxygen, what are they telling me about the oxygen? They're telling me I have 4.58 liters of oxygen. They're telling me that the pressure of that oxygen gas is 745 millimeters of mercury, and that it was measured at a temperature of 308 Kelvin. What are they asking me to find? Grams of Ag2O, question mark, grams. So normally we do grams to moles to grams. This is what we have information about, but we don't have a mass. But we have the information that we can calculate the moles. So we're going to skip this. And we're going to take this information and the ideal gas law and calculate the moles of gas. And then we can go from moles of oxygen to moles of silver oxide to grams of silver oxide. It's a variation on what we've been doing. So how are these units? Are they okay for the ideal gas equation? Two of them are. Is millimeters of mercury going to work out with atmospheres? No, we're going to have to convert that one. So we need atmospheres. And we've got millimeters of mercury. So it's 1 atmosphere per 760. So 745 divided by 760. So 0.98026 atmospheres. So PV equals nRT. We already rearranged that. N equals our PV over RT. So the pressure, 0.98026 atmospheres, times the volume, 4.58 liters, divided by the ideal gas constant, 0.0821 liters, atmospheres, per mole Kelvin. Temperature. We check out our units. Kelvins are canceling, atmospheres cancel, liters cancels. Okay, awesome. So N equals 0.98026 times 4.58 divided by 0.0821 divided by 308 equals. So 0.1773654 moles. Moles of what? Oxygen. So that's the moles of oxygen. So I'm going to jump in right here. Moles of oxygen to moles of silver oxide to grams of silver oxide. So moles of oxygen to moles of Ag2O to grams of Ag2O. So I put moles of oxygen down here, and I put moles of Ag2O down there. So my units work out. The mole ratio comes from the balanced chemical equation. 2 moles of silver oxide generate 1 mole of oxygen gas. So 2 moles of silver oxide from every 1 mole of oxygen. Then I need the molar mass of silver oxide. Was it 109, 107? 107.9. Yeah, I just had the numbers mixed up. So 2 times 107.9 plus 16 231.8. That's grams is equal to 1 mole for silver oxide. So 231.8 grams per mole. .17754 times 2 times 231.8 equals 82.307 grams. 3 significant figures. 82.3 grams of silver oxide. Any questions? That's a more challenging problem because it combines stoichiometry with the ideal gas law. That means you need to be good at doing both of them separately before you can put them together. Can you see it would be a lot more difficult to do a problem like that if you didn't understand dimensional analysis? If you couldn't use that, if you had to just kind of think it out. Yeah, I wouldn't want to do it. Yeah.
Why would we treat this? Wouldn't it just be easier to go from grams to moles to grams instead of doing all that calculation?
Well, yeah, the problem would be easier. But tell me exactly how you're going to weigh that sample of gas. That's the hard part, is the weighing of the gas. So it's easier to measure the pressure, the volume, and the temperature of the gas than it is to measure its mass. Does it make the calculation more difficult? Sure. But once you understand the calculation, I mean, it's annoying, it's tedious, but it's not that difficult. Weighing gases is a pain. It's a real pain. So that's an excellent question. We're not doing this to be difficult. Sometimes we are, but not usually. Any other questions? Okay, so this, you'll like this. This will make your life easier. Standard temperature and pressure. So STP stands for standard temperature and pressure. Standard temperature is 0 degrees Celsius. Why? Well, that's ice water. Okay? Very easy to attain without any technology. If you put something in an ice water bath, temperature 0. It's good. The Kelvin equivalent is 273. 1 atmosphere is standard pressure, which is, what usually we have in the room. So this standard temperature and pressure is easy to obtain. Yeah? I will not give you what standard temperature and pressure are. No. Yeah, you have to remember that. It's ice water at open to the atmosphere. So let's calculate the volume of 1 mole of gas under these conditions. So PV equals nRT. So I'm going to divide by P on both sides. And there's my equation, right? So N is 1 mole. And R is what it always is. .0821 liter atmospheres per mole Kelvin. The temperature now is at 273 Kelvin. And the pressure is 1 atmosphere. Do the math and see if I'm right. So 0.0821 times 273 times 1 divided by 1, 22.4. The volume of 1 mole of a gas at STP is 22.4 liters. That is a very useful conversion factor because the volume of the gas doesn't matter what the gas is. It matters how many moles of gas there are, how many particles. Because when a gas is behaving in an ideal fashion, the identity, the size of the gas molecule doesn't matter. It'll change the mass, but it won't change how the gas behaves. So the molar volume of an ideal gas at STP is 22.4 liters per mole. That is a conversion factor that allows us to very easily go between moles and liters. So now, getting back to this problem that we had, this one, where we had to do all that calculating, now we can make everything easier by taking that container, submerging it in ice water, and hooking it up so that it equilibrates to the outside temperature. Then we just measure the volume and we can use 22.4 liters per mole to get the moles. So 1 mole of any gas at STP occupies 22.4 liters. This is a little disturbing because things like this don't happen with solids and liquids. But here's 1 mole of helium at STP. Its volume is 22.4 liters. Its mass is 4 grams. 1 mole of xenon. These particles are a lot bigger, but remember there's lots of empty space. Its volume is 22.4 liters. Its mass, though, is way higher, 131.3 grams. But the number of moles at STP is the same. So gas volumes depend on the number of moles, not on their masses. We drove through, we've done it a couple times, we drive through Wyoming. Did you know that the population of the state of Wyoming is roughly the same as the population of Fresno? Without Clovis, just Fresno. The area is much larger, right? There's a lot of empty space. It's beautiful, but it's, at night, you driving on the freeway, it's dark. You can drive for like an hour and not even see lights from somebody's barn. I mean, it's just mind-bogglingly empty. So think about the people in Wyoming. Okay, so if they were all just normal-sized people, which they probably are, I didn't see many of them, think about them. Okay, but what if they were all like giants, right? Would it really matter? Because there's so much space. It wouldn't matter if they were all like 7 feet tall, 250, 300 pounds. What if you're talking about people in an elevator? You got 5 people in this little elevator over here. Would it matter if they were 7 feet tall and 300 pounds instead of 6 feet tall and 150 pounds? It would matter because there's not much empty space. In a gas, there's tons of empty space. It's Wyoming. It's not the elevator. Solids and liquids are the elevator. There, the size of the particles matters a lot. In a gas, the size of the particles doesn't matter. So let's do another problem. How many liters of oxygen at STP are required to form 10.5 grams of water? This little thing at STP is your ticket to an easier calculation. Anytime you see at STP, think, ooh, I could use 22.4 liters per mole. So, oh, cool, I could use this, 22.4 liters per mole. So what are we asked here? Question mark, how many liters of oxygen? So question mark, liters, needed to form 10.5 grams of water. Well, that's what they're giving me about the water, so I'll write that down here, 10.5 grams. So this is stoichiometry. Normally we do grams to moles to moles to grams. Here I've got grams to moles, but then at the end I want liters. So instead of grams, we're going to do liters. But because this is at STP, we can use the molar volume of a gas. So 10.5 grams of H2O. 3 arrows, 3 conversion factors. Look at the units. Grams to moles to liters. So I'm going to go grams of water to moles of water to moles of what I'm trying to find out about, the oxygen, and then to liters of oxygen. Putting the previous unit in the denominator so that the units cancel out. Now I need numbers. Well, the mole ratio, moles to moles, comes from the balanced chemical equation. 1 mole of oxygen is needed to make 2 moles of water. 1 mole of oxygen for 2 moles of water. This last one, liters of oxygen per mole of oxygen, that's this guy. 22.4 liters. You can use that for any gas at STP. And then I need the molar mass of water. So we should know how to calculate that by now. It comes out to this. So 10.5 divided by 18.016 divided by 2 times 22.4. So I'm getting 6.527. I should have 3 significant figures. And my unit is liters. And when I round that, I'm going to get 6.53 liters of oxygen gas. Any questions?